Alrighty, guys. So let's start going over the structures. If you're still drawing yours, feel free to finish up as I finish or as I start drawing them, and then you guys can check afterwards. But let's start with SO3. So while you guys are working, I took the liberty of just counting up the valence electrons. You should have gotten 24 for SO3. You got 6 from the sulfur. Oxygen is 6 each, and then there's 3 of them, so that's 18. And again, just a reminder, since I know it was a long weekend, to do the valence electron, just count the boxes in the row. So sulfur is box number 1, 2, 3, 4, 5, 6. Same thing with oxygen, and that's how you get 6 for each. All right, so for SO3, because S is less electronegative, thank you. So since S is less electronegative, it goes in the middle, and then the oxygens are going to surround the sulfurs. Okay, and then after that, we draw our first bonds in order to just connect everybody. So let's connect all the oxygens to sulfur. And if we draw 3 lines, how many electrons is that? 6. So now we're down to 18. All right, so we got to get everybody to 8, right, following the octet rule. And so let's start with the oxygens and get them all to 8. So in order to get each oxygen to 8, we need to add 6 to each of them. So that's 6. That's 12. And that is 18. And that means we're all done with the electrons. Now, what's the issue with this structure? Yes, sulfur only has 6, right? So sulfur right now does not have an octet, so we got to make it happy. So what we have to do is we need to force one of the oxygens in order to make a double bond between one of the sulfurs and oxygens. That way, we've used 24, and now sulfur is happy. Okay. Any questions about our first Lewis structure for this? Yes.
Could you add like 2 dots of sulfur or the main thing on? Because I saw for examples where you had like the large storage, they also had sulfur having
Like this?
Yeah.
But with no double bond?
With no double bond.
So like this?
Yeah.
Well, then the issue is that this oxygen does not have an octet. Yeah, so the main thing is you got to make sure everybody has an octet, which is why you need to use a double bond, because if you just do the dots here, either this is going to be missing it, or you can add 2 here, but if we do that, then we're using 26 instead of 24. Yeah. I think the image you saw might have been this one right here, because this one is going to have what you just said. Yeah, what's up, Micah?
Would it have also been right, because I don't know how resin structures work completely, but if you did like the dotted line to all 3 of the...
Yes, yeah, we're going to get to that with the resonance. So I haven't done the resonance yet, but any questions on the general Lewis structure? Okay, so like Micah said, we can do a double bond here, but if you guys remember from last time with the resonance structure, we can also force this sulfur to have a double bond with either this one or this one, right? So those are all viable options. So we can have a double bond with the top oxygen, or this one right here. We can also have this one right here. So in theory, we can have a total of 3 resonance structures for this molecule right here. So I'm going to draw them very quickly without the lone pairs, but you can have this, or you can have it with the other one. So there are 3 oxygens, so you can have a double bond with any of them, and any of these structures would work, which means that since we have multiple good Lewis structures, we can do a resonance structure. And so based on what we learned last time, you can do the dotted lines, the 1.5 bonds. So you can do the single bonds and then just draw dots. And these were the 1.5 bonds that we talked about last time. Okay, so any of these 4 structures are good options. If you drew the resonance, great job. That is the best structure, but either way, it'll work. Okay. All right, any questions on SO3? Okay, let's go to SO3 2-, but before we do that, just to see if you guys remember your polyatomics, what polyatomic ion is this? So sulfite, yeah, sulfite, okay. Sulfate is going to be SO4 2-, so if that was your guess, it's okay. Just a reminder, make sure you guys get your polyatomics done. I know I've been telling you to do this since like September, but we'll get there. We got till May, right? All right, so sulfite. Yeah, sulfite. So we got sulfur in the middle, same thing, and then we got our oxygens surrounding it. Now, for this one, we have 26, so we have 2 extra electrons to work with, right? So we're going to single bond everybody. That's a total of 6. That's going to get us to 20. Let's give all the oxygens their octet. And if we do that, how many electrons are we using to give everyone their octet? 6 each, so 3 of them, that's 18. That means we have 2 left, which is, I think, what you were referring to. Sulfur still needs an octet, so we give it the lone pairs. Make sure to bracket it and put a 2 minus. Okay, so this is going to be sulfite, very similar to SO3, but since you have the 2 extra electrons, you get your lone pairs on sulfur. Okay, so when you're looking up these Lewis structures, just make sure you're very careful. Am I looking at the ion version or am I looking at one with no charge on it? Because it will make a difference in their structures. Okay. All right, so we drew the structures. Now let's compare the bonds. So we said that SO3 goes into resonance. So these are 1.5 bonds. What type of bonds does SO3 2- have? Yeah, these are single. Now, if you remember from where we ended up, which one is shorter?
1.5.
1.5 is going to be shorter. It's a stronger bond. So the shorter one is going to be for SO3. Okay, and that would be the answer to your question. If you got that, great job. Okay, so just a reminder, 1.5 bonds are somewhere in between single bonds and double bonds, and it has pretty much like in-between properties in terms of strength and length. All right, that's pretty much all we're gonna do for resonance, but any questions on that? Okay, so we've talked about octet rule and how it's important to get everyone their octet, but there are some exceptions to the octet rule, some very important ones that we're gonna talk about. And these are ones you're expected to know for the AP test, so apologies, but another thing that you gotta memorize, okay? Don't look at me like that. I don't make the AP test. All right, so 3 main exceptions. The first exception, and you might want to jot this down, and again, you can paraphrase it. First are molecules that have an odd number of electrons. So if you notice, all the molecules we've been drawing so far have an even number, but there are some molecules that have an odd number of electrons, and they're going to have odd Lewis structures. Okay. Okay, so we're going to jump straight into an example. I'm not going to have you draw this. Instead, I want you to look at these 2 structures. The most common molecule on the AP test with an odd number of electrons is NO, nitrogen monoxide. And if you look at NO, these are the 2 viable options for NO. But if you look, you can't have an octet for both elements, right? If you look here, nitrogen does not have an octet because it has an odd number, and here oxygen does not have an octet. So what I want you to do, take a minute, I want you, based on what you know so far, I want you to jot a quick explanation. Which one do you think is better? So we'll call this let's call this structure 1, and we'll call this structure 2. So make a choice. Which one do you think is the better Lewis structure? And then write a quick explanation why. There are 2 really good answers that you can give, but let's see if you can get both, that would be great as well. But see if you can get at least one of the explanations why, based on what we've talked about in this unit. Take about a minute or so, pick an option, and then write your explanation for why you chose that option. All right, so the dominant structure is 1. Now, I said there were 2 good explanations, so let's talk about why 1 is the best explanation. The easiest explanation, I believe, is that oxygen is more electronegative. Yeah, so that is the best easy one. Great job. So oxygen is more electronegative, and that's the one I actually want you to think about first. It's because it'll be helpful for the rest of the unit. So more electronegative, it's going to pull the electrons to itself. The second reason is going to be because of the formal charge. If you thought of that, great job. So let's look at the formal charges. If you remember, formal charge is the formula we talked about. It's the valence electrons, so nitrogen is 5, minus the lines next to it, so nitrogen has 2 lines, minus the dots, that's 3. 5 minus 2 minus 3 is 0. So nitrogen is 0, which is what we want on everybody if possible for formal charge, right? Oxygen right here, 6 valence electrons, 2 lines, 4 dots. That'll get us to 0. And since both of them have a formal charge of 0, this is the dominant structure. Okay, if you look at this one, however, it's going to be 5 minus 2 lines minus 4 dots. Nitrogen has a -1 formal charge, which we don't want, right? The more electronegative one should have the negative formal charge. And oxygen right here will be 6 minus 2 lines minus 3 dots, which will be +1. So this is a no-no structure. So those are the two options you could have come up with. Obviously, number 1 is a lot easier, and I would recommend thinking in that way because it'll be helpful for the other stuff later in the unit. But any questions on 19? Okay, great job. It looked like everyone pointed up 1, so that's good. All right, so that's the first exception to the octet rule. It's when you have an odd number of electrons. Let's go to the next exception. So there are some atoms that can have less than 8 electrons. Okay, there are some notable examples, but you only really need to know 2 of them. We already have been using one of them a lot, which is hydrogen, right? Hydrogen does not have an octet. Hydrogen has 2 valence electrons. That's why we can only have 1 line next to it. The other notable exception is going to be boron. Okay, boron can have 6 or 8 valence electrons. Okay, 6 or 8. 6 or 8 valence electrons. So we got an example right here. You look at BF3 right here. It has 6, but we can have this molecule and you have 8 valence electrons. So either can work. Again, those are the 2 notable exceptions. You already know hydrogen very well, so just remember boron. Okay. All right, and for the next example, I want you to take out your periodic table because it kind of helps visualize it. So make sure you have your periodic table handy. But the next notable exception are molecules where an atom can have more than 8 valence electrons. Okay, and we call this hypervalence. I just like mentioning that because it's a funny word, hypervalence. All right, so hypervalent elements, if you look at the periodic table, I'll tell you where they start. So if you remember, as you go down the periodic table, the elements get bigger, right? More shells and whatnot. And so once you get to elements like phosphorus, they are big enough where they could accommodate more than 8 valence electrons. Okay, so if you want to make a quick note somewhere, starting with phosphorus, you can start having more than 8 valence electrons. Exceptional, well, given the fact that they're not that electronegative. So for example, chlorine does not want to have more than 8 because it's electronegative, very electronegative, so it likes to have its own electrons. But elements like phosphorus and sulfur, if you want to make a note, phosphorus and sulfur and xenon, these are the 3 notable ones. These are the 3 that usually you'll get examples of having more than 8 valence electrons. Phosphorus, sulfur, and xenon. Technically, chlorine can. It's big enough, but because it's so electronegative, it tends to not. Oh, and then iodine and bromine. Sorry, forgot to mention. These ones don't come up too often as hypervalent, but you do see some examples, so I just want to cover all the boxes for you guys. Those are the 5 that you'll see, but the ones that you'll see the most are going to be phosphorus, sulfur, and xenon as the hypervalent elements. And again, the reason why they can have more than 8 valence electrons is because they're so large. Their valence shell is really big, so you can fit more than 8 in there. Typically, you're going to go either 8, 10, or 12. Okay, you're not going to see any examples with more than 12. So if you want to make a note of that as well, 8, 10, 12. So let's take a look at a couple examples of hypervalent ones. If you take a look right here, XeF4, you see Xe, right? It's surrounded by 4 fluorines, and it has 2, 4, 6, 8, 10, 12 valence electrons. If you look at phosphorus right here, it has 10, and sulfur has 12. Okay, so just some examples. These are some molecules you might be asked to draw on your assignments or on the AP test, so just want to give you a heads up. These are the hypervalent ones. All right, so with that being said, I want you to try an example, and I'm kind of giving you a big hint. This is going to have a hypervalent central atom. See if you can draw XeF2. Same thing as before, count up the valence electrons and see if you can get some to octet, but if you have extra, who can you dump it on? So try that out. I'll give you about 2 minutes to draw that, and you can compare with your neighbor. Alrighty guys, let's draw XeF2. So Xe is kind of interesting for the valence electrons because if you look, we have to use one of those weird exception rules for the valence. Another exception for you. We're going to start row 5, 1, 2, and then if you remember the transition metals, we skip because it's the D subshell. And then we go 3, 4, 5, 6, 7, 8 valence electrons for xenon. Okay. And then for fluorine, it's the same thing as before. It's going to be 7. So we're going to take a look back at XeF2. Like we said, xenon gives you 8. Fluorine gives you 7 each, so that's 14. So that's going to give you a total of 22 valence electrons. Okay? So a lot of electrons for a pretty small molecule. Now, if you think about it, which element is going to go in the middle of this molecule? Xenon. Why is xenon going to go in the middle?
Because fluorine is the most electronegative.
Yeah, exactly. Good. You're glad that you remember. Fluorine is the most electronegative, so it very rarely wants to be in the middle of the molecule. So we're going to make our connections. So 2 lines. That's going to get us to down 4 to 18. If you look at fluorine, it wants its octet, right? So we're going to give it 6 valence electrons. We drew 6 twice, so that's going to be 12. And that's going to get us down to 6. Now, if you look, fluorine is happy because it has its octet, but xenon is not. So let's give it its octet. But to get its octet, we have to use only 4, right? So we still have 2 left over. Okay, but we talked about xenon already. It is very large, so it's going to be hypervalent, so it can actually accommodate more than 8 valence electrons. So we'll have a total of 10. Okay, so xenon right here will be the hypervalent element, and it can have 10 valence electrons. So that's how that structure can work out. All right, so let me zoom out real quick. So let's move on. So what I want you guys to do is title this next section, Strength of Covalent Bonds. So now we're going to actually start putting numbers to how strong these bonds are. So we talked about how when these elements form bonds with each other, the energy is stored in those bonds, right? Now, based on the strength of the covalent bond, it talks about the stability of the molecule. And what we're going to talk about now is something called the bond enthalpy. Okay, so if you remember enthalpy, the variable that we use is delta H. So we're going back to enthalpy. And if you remember, what's the unit of measurement used to measure enthalpy? Yeah, joules or kilojoules. So this unit, we're going to talk a lot more in kilojoules, so just make sure you're aware of that. So we're going to have a number and kilojoules. And what this bond enthalpy is basically how much energy does it take to break that bond? Okay, energy to break the bond. All right, so we're not going to get into the super technical definition. You can read more about that in the textbook if you would like. Yes, like everybody keeps up with the reading, right? Everyone reads before class, right? So I'm just reviewing the information for you all the time. All the time. All right. All right. Okay, so the way bond enthalpy works is different connections have different bond enthalpies. So for example, and I want you guys to write this down. Let's say, for example, oh my goodness. Okay. Let's say that you have this molecule right here. So let's say we have this. You don't need to draw the molecule, but you see how there's a single bond between these F molecules, right? Or these F elements. This specific type of bond, the F single bond, has its own specific bond enthalpy. So the way that we write it is we write the letter D, and then we put parentheses around the type of bond that we have. This I do want you to write down. And then that's going to give you a specific value in kilojoules per mole. Okay, so different bonds have different bond enthalpies. So for example, for FF, this value is going to be 159 kilojoules per mole. Now, that's going to be different from the bond enthalpy of a, let's say, C-C bond, a carbon-carbon single bond. Okay, and that value is going to be 347 kilojoules per mole. So different bonds have different bond enthalpies, okay? So what we're going to do right now is we're going to look at a molecule. I'm going to show you guys how to count up the bond enthalpy. So for example, let's say that we have this molecule right here, CC, and I want you to draw this on your paper. Just kind of pulling this out of my brain. But let's say that we have this molecule, C2F6. C2F6. And this is what the structure looks like. Now, in order to calculate the bond enthalpy of this molecule, what we have to do is we need to count up how many of each bond is in this molecule. So let's take a look at this molecule. If you take a look, there are a bunch of carbon-fluorine bonds, right? So there's a CF bond right here, another one here, another one here, so on and so forth. So we're going to have a total of 6. So we're going to have a total of 6 CF single bonds. Make sense, everybody? Just looking at the structure, there are 6 different CF single bonds. And if you look, the other type of bond that we have is the CC single bond, right? So there's going to be a CC single bond. So this molecule is made up of 7 different bonds. You have 6 CF single bonds and 1 CC single bond. Make sense? Okay, so I am going to give you the value of the CF single bond. The CF single bond is going to be 485 kilojoules per mole. Based on that, I want you to take a minute. I want you to calculate what is the bond enthalpy of this entire molecule. Okay, so we got the CF single bond number right here, the CC single bond number right here. I want you to calculate the delta H of the entire molecule. All right, so if we take a look at this molecule, we're going to calculate the bond enthalpy. Like I said, we're just going to multiply the bond enthalpy for each bond by how many there are. So a CF single bond is 485, and there are 6 of them. So we just multiply that by 6. And so to break all of the CF bonds, it's going to take 2910 kilojoules per mole. And then the CC single bond is 347. So if we want to find the bond enthalpy of the entire molecule, I just messed up. Thank you. We just need to add them up. So 2910 plus 347, that'll give you 3257 kilojoules per mole. Okay, and so that's how you find the bond enthalpy of a molecule. Pretty easy, right? Now, you do not need to memorize these bond enthalpies. There will be a chart given to you. So if we look back at the workbook, when you are doing your assignments, it's going to be on page 13 of the workbook, just so that you have a quick reference when you're doing your assignments. But if you have this on the test, which you will, it will be given to you. Okay, I will provide them for you. Okay, thank you. I'm not the best, but I appreciate it. Yeah, so if you have this type of problem in the AP test, they'll give you like a little table on the side. Not this exhaustive, but all the ones you need will be on there. Yeah, but for your homework, I know it tells you to go like appendix something to find it, but instead of flipping through the notebook, just come here. It's on page 13. All right? All right, now, it does not stay that easy because I respect you too much to keep this problem that easy. So instead of just looking at individual molecules, we are now going to be looking at something called enthalpies of reaction. Okay, I know, so fun. And it's exactly what it sounds like. Based on the structure of the molecule, what is the enthalpy of the reaction? How much energy is, what's the net either release or absorption of the reaction? And it's very simple. It follows this formula right here. I want you to write it down. The delta H of the reaction, and this is a little different than what we've been looking at previously. Usually when we look at delta, right, when we look at the triangle, it's always final minus initial. But this is the only equation where it is not final minus initial. Instead, delta H of the reaction is the sum, right? The sigma symbol means sum. So add up all the bonds broken. And if you think about it, what are the bonds that you're breaking? It's the ones on the reactant side minus the bonds that are made, the product side. So make sure you write this down. Make sure you put a star next to it or something, because this is the only time where we have a delta reaction or equation where it is not final minus initial. This is the only time it will be initial minus final. And a lot of students mess up on this part and lose points because we always do final minus initial. But this is the one time we don't. And it's because it's bonds broken and then formed. Yes?
So for all,
all right, so if we take a look at the reactant molecule N2H4, the structure, you have one NN single bond and 4 NH single bonds. Everybody good with that? Okay, so we're going to look back at the chart. I'm not going to pull this up on the screen just because it's going to take up space, but look at the chart on page 13. And if you look at the NN single bond, it should be 163 kilojoules per mole. The NH single bond is 391, so we're going to multiply that by 4. Now on the product side, you have one NN triple bond. And if you look on the chart for that, that is 941. Now, before we move on, what do you notice about the single versus the triple? What do you notice about their bond enthalpies? Yeah, triple's a lot higher, right? Which goes with what we learned, that triple bonds are stronger than single bonds. The value is a lot higher. All right, and then the HH single bond is going to be, the HH single bond is going to be 436, but there's 2 of these molecules. That same thing of having another one, so we're going to have to multiply that by 2. So those are our values. So let's take a look at the NH. That's going to be 391 times 4. That'll be 1564 right here, plus the 163, and that's going to be 1727 for the reactant side. Okay, that's the broken bonds. So these are the broken bonds. Now for the formed bonds, we're going to do our hydrogens first. So 436 times 2 plus the 941. These are the ones that are being made. So that's going to be 1813. And these are the made bonds. So in order to get to the delta H, we just need to subtract them. But if you remember, it's broken minus made. So we are going to do 1727 minus 1813. That'll give us a value of negative 86 kilojoules per mole. So is this exo or endo? Is this exothermic? This is a chart that tells us the three-dimensional shape of the molecules and how to figure them out. So before we do that, let's look up here. Actually, my bad. We're not looking at the chart yet. We're going to do an FRQ where we put everything together. My bad. I forgot about this. I forgot that this problem was on here. So this is an example of a problem that kind of puts together everything that we've learned from this unit, but it also puts together some of the things that we learned from previous units. So it's a lot of fun. So we're going to do part A together because it's been a while since we did this type of problem. But let's look through the description. So it says phosgene. So it's a chemical we probably don't know. It's a substance used in poisonous gas warfare during World War I. Very interesting. Okay, it is named because it is prepared by the action of sunlight on a mixture of carbon dioxide and chlorine gases. So basically, People use carbon dioxide, chlorine gas, they put in a container, they put in the sun, and it made this poisonous gas. Very fun. Okay, its name comes from the Greek words phos, light, and genes, born of, so that's not that important for our problem. But it gives us this elemental composition. 12.14% C, 16.17% O, and 71.69 chlorine. And the molar mass is 98.9. Now, if you look at this, do you remember what type of problem this is? It was like in Unit 2. It is an empirical formula. So fun. Empirical formula. So we're going to do part A together because we haven't looked at this since our first exam. Second exam, we did this. But let's look at how to do an empirical formula. So whenever you're doing an empirical formula problem, the first thing you do is you're going to assume a 100-gram sample. You guys might remember this. Good. And the reason why is because then we can just easily convert the percentages to grams, right? So if it's 12.14% carbon, that means that we have 12.14 grams of carbon. If it is 16.17% oxygen, that means we have 16.17 grams of oxygen. And then our 71% becomes 71.69 grams of chlorine. And the first thing that you want to do is you want to convert all of these to moles. So I am going to give you about a minute or two. See if you can convert all of your grams here into moles. You're going to need the periodic table for that and your calculator. So go ahead and take those out. Alrighty guys, so you should have gotten these values for your moles. Just divide by the molar mass on the periodic table. Everybody chilling with that?
Yep.
Okay. So what we're going to do now is we're just going to assume that these are moles and we're going to make our empirical formula. So C will be 1.01. O will be 1.01. I know some of you guys are like, I know what it's going to end up as, but I'm just trying to show you for the sake of example. And then what you do is you want to divide by the smallest number. So you are going to divide by 1.01, and that will give you the empirical formula C1O1 Cl2. So Cocl2.
I like that.
All right, so remember, this is our empirical formula, so we're going to label that. It tells us the molar mass, though, of the actual formula, the molecular formula. That is 98.9. So what we're going to do is we're going to see what the molar mass of the empirical formula is. Well, it's 35.45 for the chlorines, and there's two of them, plus 12, plus 16. Well, I guess the empirical formula is the molecular formula. So we're going to write that this is also the molecular formula, because if you add them all up, it's still going to be the same structure, or formula. So Cocl2 will be the formula of phosgene. Alright, so that's the review from previous units, and as you can see, the AP test, and I think I stole this from the AP test. I don't remember what year, what version of the test it was, but this is the type of problem you'll see. But as you can see, it's taking things from the previous units, and it's going to combine them with the stuff from this unit now. So what I want you to do is I want you to work with the person next to you, or maybe in a group of 3, that's fine as well. I want you to draw the Lewis structures that phosgene can be. So based on what we learned, I want you to draw the structure of phosgene. It tells us that you can have 3 structures. So at least try to get one of them, and then with your partner, see if your partner gets a different one. But see if you can at least come up with 2 or 3 of them. And then I want you to finish the problem, write the formal charges to figure out which one is dominant, and then do the bond enthalpies to do the formation of phosgene from CO to Cl2. So kind of a big problem, but let's see if you all can finish it on your own. I'll give you about 7 to 8 minutes to do this, and then I'll be walking around to see if you need any help, all right? All right, so there are 3 possible Lewis structures. 2 of them go into resonance with one another. So if you take a look, you can have carbon. You have to have carbon in the middle, and then you can have a double bond with either of the chlorines. So that's your 2 resonances right there. And the oxygen has its lone pairs. Okay. The other option that you have is you can make a double bond with the oxygen instead. So basically, the differences is where does the double bond go? Does it go with the oxygen or does it go with one of the chlorines? And that's your 3. Now, let's talk about which one is dominant. So we're gonna take a look at one of these, and since the formal charge will be the same for both of these because it's kind of the mirror image of one another, we can just do one of them. Let's take a look at carbon right here. Carbon's formal charge will be 4 valence electrons. How many lines are connected to carbon? 4. How many lone pairs does it have? None. So this carbon right here will have a formal charge of 0. Okay, good start. Let's take a look at oxygen right here. It has 6 valence electrons. How many lines does it have next to it? 1. How many dots? 6. So this is going to be -1. Let's look at this chlorine right here. Chlorine has 7. How many lines next to this one? 2. How many dots? 4. Okay, so that's going to be +1. And then I'll give you the last one right here. It'll be 7 minus 1 line minus 6 dots, so it'll be 0. So we got the formal charges for everybody. Now, this isn't the ideal one because ideally we have everyone at 0, right? But it's possible not to have everyone at 0, so let's take a look at the other structure. If you look at the carbon, it's the same thing, so this is going to be 0. Let's start with the oxygen. How many lines are next to oxygen? 2. How many dots? 4. So this is 0, so better start. And if you look at the chlorine, it's 7. How many lines? 1 and 6 dots, 0. So which one is dominant, top or bottom? Bottom. This is the dominant structure right here. All right, so that's how you use formal charges in order to get the dominant structure. All right, everybody, we will take our 5-minute break. 5, and then we will come back and we will do part D before we move on to the next section. All right, so what we're going to talk about next is what the molecules look like in 3D. So we're going to take a look at methane, CH4 right here, and usually if we draw the Lewis structure, we just draw it like this, right? Just a flat shape. However, reality is not two-dimensional, and so we want to take a look at what these molecules look like in 3D. So we're going to make methane right now with our crafts. So what I want you to do is pick one of your foil balls. Hey guys, let's focus. So take one of your foil balls, and this is going to represent your carbon. Okay, this is the one that goes in the middle. So I want you to look at it, and I want you to tell it, you are carbon. Okay, you are carbon. Okay, next, what you're going to do is you're going to get a toothpick, and you're going to stab your carbon on the head, okay, the top. Okay? And this is going to represent, don't say sorry. This is going to represent the single bond that's going to connect to a hydrogen. And this one by itself is going to be hydrogen. So you're going to tell it, you are hydrogen. Yes, yes. You guys sound like a cult just now. Alright, so everyone see this? This is carbon and hydrogen. Now, we're going to make another single bond. So I want you to get your 3 toothpicks. And usually, don't do this part. Usually, if we draw it, it's going to look like this, right? It's kind of like a cross shape. However, reality is not two-dimensional. And so we have to think about some of the 3-dimensional things that happen with these bonds. Now, if you remember, what are these bonds made out of? Electrons, yes. Now, what do electrons do to one another?
They repel.
They repel. So, what actually happens is these bonds push each other away so that they are as far away from each other as possible, and this cross shape is not as far as possible because there's another plane that we can work with. So, I want you to take your 3 toothpicks, and what you're going to do is you're going to make this shape right here. So, kind of like a obtuse angle. And then one of the toothpicks is going to go in the front.
Looks like a tripod.
Yeah, like a tripod. And one is going to go in the back. And this right here is the 3D shape, exactly. The 3D shape of methane. Because what happens is the electrons in the bonds push each other away. And so this is what it's going to look like. I'll put the rest of my hydrogens right there. And this is going to be your methane molecule. Okay? So, even though we draw the Lewis structure like this, it looks like this in 3D shape. Okay? This is what it looks like. Alright, so I want you to look at it and say, you are methane.
You are methane.
Say, I am methane. I am methane. We are methane. Yes, yes, yes. You guys are. Alright, so that is my Christmas gift to you. Merry Christmas, everyone. Enjoy your methane. We are not, yeah, whatever. I go to Target and the Christmas decorations are up, so it's Christmas. Alright, so that is what it looks like. Now, we're going to talk about how to draw this on paper because there is a way that we represent it. So, once... Oh my god, that bell is dying. Alright, so once you put down your methane, let's draw what it looks like. So, first thing we're going to do is we're going to label this. This is the 2D version of methane. Okay, I know you love your methane, but let's put it down and let's start taking our notes. So, this is the 2D way of drawing methane. I'll give you guys a second to draw that. Methane is just flat like that. This is the 2D version. This is the way that we've been doing it. Okay, but now we're going to learn to draw it on paper the 3D way. And honestly, I personally don't think it looks 3D, but some smart dude told everyone to do it like this, and this is how we do it now. So, the 3D way, we're going to draw the carbon in the middle again, and we're going to draw the hydrogen going up. Okay, so that one stays the same. But if you take a look at your 3D methane, you notice how one of the hydrogens goes out to the side, right? So we're going to draw one going out to the side, like that. Now, when you look at the hydrogen going out to the side, so this angle right here, you see how one of the hydrogens comes out towards you, right? The way that we represent that is we draw a triangle, but we fill the triangle in. And this filled in triangle means it is coming out of the page. So it's coming towards you. It's attacking you. Okay? And then if you look, I don't know if you can see it here, but there's one hydrogen going away from you, right? So into the paper. And the way that we go into the paper is we draw 3 dashed lines like that. And this is the 3D way of drawing methane. Okay? 3D way of drawing methane. So one of the hydrogen goes out of the page, one of the hydrogens goes into the page. Right? And that is how you draw the 3D structure of methane. So we're going to be drawing the molecule XeF6. XeF6. So we're going to draw a xenon with 6 fluorines connected to it. Now, this one right here will have xenon in the middle, and we're going to have 1 fluorine going up and 1 fluorine going down. Everybody good? Now we have to draw 4 more fluorines. So the way that this structure will look is there's going to be 2 fluorines going into the page and two fluorines coming out of the page. So I want to show you this just so I can show you that you can have multiple of these shaded and these dashed lines. Okay, so I didn't give you enough toothpicks to make this, but you can kind of visualize what it looks like, right? 2 going up, 2 going towards you, and 2 going back. Alright, so that is how you draw the 3-dimensional pictures. Let's take a look now at some vocabulary, and then after that I'll show you guys how to use a chart, and then we'll be all done, okay? I know it's a lot of talking from me today. So, what I want you to write down are these 2 terms right here, bonding pair and non-bonding pair. Okay, and bonding pair just means that it's a bond. It's a connection to another atom. And non-bonding pair are lone pair electrons. And what we do is we're going to be looking at how many of these an element has in a molecule, and that's going to allow us to figure out what shape it makes. So if you take a look at your methane, let's take a look at the central atom, the carbon, right? If you take a look at the carbon, you see how that there are 4 connections to 4 different elements, right? So if you look at carbon right here, what we're going to write is we're going to write that there are 4 bonding pairs. Okay, so 4 bonding pairs. Do you see any lone pairs on the carbon? No, so there are 0 non-bonding pairs. So I'll just write MBP, okay, non-bonding pairs. So what this is going to allow us to do is we're going to use that chart that I gave you guys 2 Christmas presents today, to figure out what the shape of methane is. So we're going to go to our chart, and you're going to look for 4 bonding and 0 non-bonding. So you're going to look right here, and that's going to tell you that methane is sp3 hybridized. We'll talk about this later. And the shape's name is tetrahedral. Tetrahedral. It also tells you the angle of the bond. So if you look at your methane molecule, you see how there's an angle between the bonds, right? The angle of that bond is 109.5, and that's the maximum amount of space the electrons are going to make with one another. Okay? So that's how you can use this chart in conjunction with the Lewis structures to figure out the geometry, and that's going to tell you what shape the molecule is.